Hello everyone, today I will deliver a lecture on subsurface exploration. So let's start the lecture. The lecture is based on theoretical, so it will be boring, but it has contained some mathematical solution also. So let's start. At first, we have to understand what is subsurface exploration. The subsurface exploration can be defined as the process or technique identifying layer and deposition of soil, rock, and obtaining their physical characteristics on which, through which, by the side of which, or using which, and any purpose of structure by will be built. So here is some purpose of subsurface exploration. So at first, uh, number one is the selecting type and depth of footing. Number two, the evaluation load bearing capacity. Number three, the estimating settlement. Number four, determine the lateral earth pressure. Number five, determine the location of the groundwater, and then the determine solve idea foundation problem and explosive characteristics, and then select the suitable construction technique, and then assert the suitability of construction material, and finally the investigation of safely existing structure and to suggest the remedial measures. As a some exploration program, we can see here the geotechnical subsurface program comprised of the several steps can be summarized, which is the preliminary information, recognizes field investigation, laboratory analysis, registration, and prepare subsurface report. Okay, here is we can see the collecting process as if for the construction of building, the estimated column load and their spacing, and the local building code such as ACI 318, ASC 7, BNBC, IBC, so on, and basement requirement. And for building, the span length of bridge and loading on pier and loading on abutment. So reconnaissance, we can see the different type of reconnaissance. The most important thing is the field investigation. So the field investigation phase in the exploration program preliminary consists of planning, drilling, logging, sampling in situ, and observing. So I am skipping this. So selecting borehole number. So I will select the borehole and location and number. Type is building, the spacing and number of borehole. For project consists of the smaller area, minimum one borehole on each corner. Project for consists of the bigger area. So spacing range from 30 feet to 100 feet, and commons is the distributed borehole among the entire site. So if I summarize that, in the most of the cases we are construct the building. So for small area of building, we have to minimum one borehole. The each corner means uh, if the plot is the square, then we have to take the four borehole. On the other hand, we can see another project which is the bigger area, so minimum one borehole of each corner, and the spacing range from 30 feet to 100 feet. Okay, say another, we can see the bridge. For the bridge, the location of the bridge, pier, and abutment, it must be taken for the borehole. And road and abutment for 800 feet to 1600 feet, and residential subdivisional 600 feet to 1600 feet, and dam 10 feet to 200 feet. Okay, so this is the important things for the general guideline of selecting borehole depth, which which are up to the depth where the distribution induced approved stress become 10%, and the distributed induced stress at the foundation level, and another point is that usually the base of the foundation level depth at least at least 2.5 times of the minimum dimension of the footing. And then in case of the requirement pile foundation, the depth of borehole should be extended up to the depth where the hard or relative harder strata is encountered. And then number of construction building project up to 5 or 6 stories in Bangladesh or India region, the borehole depth are usually on the order of 50 feet below existing ground level. But if the encouraged subsoil during the drilling and logging are found be of very loose, and loose means sand and silt, and soft means clay in nature, borehole depth required could be the order of the even 100 feet. So this is our provision of code BNBC or ASC7 or other code as is required for web to borehole 100 feet. For any excavation project, borehole depth should be at least 2 times of the excavation depth, and for highway embankment the excavation should be 5 to 10 feet, and embankment project borehole depth should be 10 to 100 feet base. Okay, so let's see here the some drilling and logging. Angle drilling means angle boring, wash boring, rotary boring, percussion boring. Angular boring is this like this. This is the post angle and borehole drill hole. And we can see here the soil is a mechanism part which is work in civil engineer. On the other hand, soil, the mineral or composite part is work on the petroleum engineer. So on soil is building, in soil is SPT, by soil is retaining wall, through soil is unknown, and off soil made by soil bricks. We can see the intensity of force is equal to pressure. So pressure equal to force per area, as we know. So geotechnical investigation, we can investigation why and where, and slope stability. And some of the major features we know: the foundation system, earth retaining system, subsurface excavation system, slope, and the effect of foundation, slope, size, depth, and so many things. Water we can see the incompressible and higher compressibility. So we cannot compress the water. That's why we can call the higher compressible. Okay. So we can see here is an example. So justify the following footing given below as a geotechnical engineer. We can see the footing is given here. The column size is 1 feet, and applied load is 100 kip, and we have to find the footing size, and the allowable bearing set capacity is given 4 KSF. So you can see given footing load is 100 kip, and assume column size 1 feet by 1 feet, and allowable soil bearing capacity 4 KSF, and footing size. We have to find out the footing size. So we know the stress is equal to force per area, and putting this value and found the stress 100 KSF. So 100 KSF is greater than allowable soil bearing capacity. So upcoming stress is greater than the soil bearing capacity. That's why column will be punched and footing will be failed. So we have to increase the soil bearing capacity of footing and size, material strength such as F prime C and Fy. Now we can see the stress demand and stress equal in supply. So demand equal to P, and supply equal to allowable. So demand is force per area, and allowable is given on the right hand. So we know the force is 100, and area we have to find out, and allowable is we know 4. So the footing after the calculation, footing will be 25 feet square, or feet per feet into feet. The footing, the size of footing in feet into feet. So let's see another example. Here the factor of safety is given 2 and 3, and average 2.5. Factor of safety surplus plus demand we have calculated here. So we know the load is 100 kip, so it will be kept, and size of footing 12 by 12 inch, and bearing capacity also 4 KSF. If the column rests in the directly over the soil, the factor of safety will be we know the 4 KSF allowable divided by soil applied load, and it is 0.04, which is less than 1. So we know the we know the supply, which is demand D, which is D, and the supply is S. So supply equal to demand S. So demand we can know force per area, and supply is supply. And putting the value P is 100 and allowable is 4, and found the area of footing 25 feet square, which is 5 into 5 feet. So allowable bearing capacity, apply pressure. Now factor of safety, we know the supply divided by demand, so this is the 4 divided by 4 is 1, but the factor of safety should be 2.5. We know the factor of safety must be 2.5, but we have found 1, so we have to increase the factor of safety. So that's why we have if we induce the supply, then the factor of safety will be induced. So let's see the allowable. So we know the allowable equal to force per factor of safety equal to supply divided by demand. So if we take the this interchange, then it will be allowable divided by Q by factor of safety, and Q allowable is Q ultimate. So Q ultimate we know 4, and allowable is 2, factor of safety 2, so the allowable is 1.6. So now we are putting this demand divided equal to supply. So demand equal to force by area, and supply 1.6, and consequently we have found the area of footing is 62.5, which is 8 feet by 8 feet. This is for remind that this is for factor of safety is 2.5. Okay, so let's see an example. So for EBLP by A is 4 KSF, and vertical stress 100 into 10 equal to 1 KSF. We can see the picture here. The applied pressure is higher than the overburden pressure, so foundation bearing capacity level, so which is a critical zone. Okay, so let's see. Here is the effect of foundation shape, size, and soil depth, B into L. Okay, let's see here. We can see the sand. The C is higher C because the 10 phi is more. C is also higher because clay. Liquid limit is 150 and liquid limit 30. The liquid limit, which is liquid limit is higher, the expansion of soil will be more. Here we can see another. Find the stress of the footing given below the figure. 100 feet from footing base and footing slope is 2:1. So let's see. The stress as foundation or 10 feet below the EGL. So this is the given in question. The foundation is depth is 10, and the footing depth is 10 into 12, and soil bearing unit weight of soil 100 feet per cubic feet, and soil bearing capacity 4 KSF, and this is the 100 feet, and the slope is 2:1. So we can calculate the vertical stress at 10. So gamma prime into Z, which is 1 KSF. Force at the foundation level 10 feet below the EGL. So force is stress into area. So stress is given soil bearing capacity 4, and area is given 10 into 12, which is the footing area, and found 408 kip. So so stress at 100 feet below the EGL when the footing slope is 1:2. So we know the P into B by B plus Z and L plus Z. What is B and what is L? This is the L, and B B into 10 and L into 12, and Z is 100. Is a vertical vertical length Z 100, and B and L is the footing size. Okay, so we are putting the load of 480 we have found here 480, and B is 10 we have known, L is 12 we have known the footing breadth and length, and Z is the vertical vertical length of the soil where will be stress will be induced, which is 0.04 ksa. So we can see another example here. Here we can see the same example is given here. 400 keep, and footing length is B into L, 10 into 10, Z equal to unknown, so 2:1, so this portion will be Z by 2 and this portion will be Z by 2, and P equal to P by A, stress equal to P by A is 4 kSF. So this is the 10% of allowable stress, which is force into B plus Z into L plus Z, and allowable bearing capacity is 10% and found 21.62. So if we add this portion to footing base level to existing ground level, the depth is 10, then it will be 31.62. So we can see here another example which is given. Find the effective stress at the point Z and following the given below when the water table is CGL and sandy soil is Quen. So this is the Z, and the depth is 10 feet, and the soil all the parameters given, and found the Z is 10 feet. Effective stress in 10 feet is 0.57, and the stress shear stress is C plus psi stress into 10 phi, and found 0.54. And the similarly we have found the another example, and stress equal to 120 and Z equal to 10, and effective stress at 10 feet is 1.2 kip, and shear stress 1.12, when the C is 0. So this portion C is 0. On the other hand, we can see here the C is also 0. Okay. Here is a wash boring. We can see the picture, and rotary boring, precursor boring, drawing. I am skipping this. And this is the important is disturbance sample. We can use the sampling. It is involved to collecting the soil sample at the desired depth, usually at 5 feet below 5 feet depth of the interval. Two type of sample. So disturbed sampling or relatively disturbed sampling. Application cohesive soil only for clay. So we can see the disturbed sampling, which is clay, using the Shelby tube SP sample and using piston sample. So Shelby tube we have been use the moderate soil to hard, cohesive and thin, while Shelby tube and commonly used. The sampler geometry is given. D naught is outer diameter is 2 to 3, and Di is inside diameter 147.63, and length of the tube is 16. So degree of disturbance we have, if we calculate the degree of disturbance we have found, I am calculating here. So we know the degree of disturbance. DO means outer side of dia, outer side into inside dia into inside dia square into 100. So we have putting for Shelby tube we have putting all this value and found 8.96, which is less than 10. Okay, so we know the if the degree of disturbance is greater than 10, that will be the soil will be disturbed. So we can see this is the okay. And another for split sample sampler, the inside outer side and inside dia is given here, and found 1.54, which is greater than much greater than 10%. So this is the disturbed sample. When the degree of disturbance is less than 10, sample is relatively undisturbed. If the soil is greater than 10, then soil is disturbed. Okay, so let's see another. In situ testing, we know the SPT, standard penetration test, which is SPT, and bend shear test, BST, and cone penetration test, CPT, and pressure piezometer test was PMT, and dilatometer test, DMT. So in situ test is very popular is SPT. So in our region, in Bangladesh, especially India and USA, are using the SPT value. Also Japan also. So let's see what is the SPT. SPT, the most of the cohesive used for the cohesion-less soil to collect the disturbed sample in situ strength provided by good correlation angle of internal friction and cohesion less soil. Also used for cohesive soil to have the estimated in situ length. In situ length of cohesive soil, cohesive are not always relative. Result field the test are needed to be verified the performing unconfined compressive strength using disturbed sample obtained by Shelby tube sampler. So this is the figure we can see the true drill, and the steel sampler tube is 2 inch spirit and harder steel cutter shoe. We can see here in the picture, and a 140-pound hammer is used to fallen to drilling rod and maintain drop approximately 30 inches to the create blow of drilling rod. Due to the blow of the drilling rod, the split spoon sampler SSS attached to the tip of the drilling rod penetrate the soil. The test is conduct 3 consecutive penetrations, so 1, 2, 3, and each of the consisting 6 inches. So this we can see the if we see the hammer is dropped, one hammer is dropped, the weight is 140 and drop for approximately 3 inch, and this is the split sponge sampler and drilling penetration soil and test the contacted 3 consecutive. That means this weight will be falling 3 times. Okay, and consisting 6 inches, so it will be penetrate 6 inches. 6 inches we will consider 6 inches only, and first drop we will not consider. The first 6 inch penetration is ignored, avoiding the soil disturbance, and the same number of blow n is required to the 12 inches. 6 plus 6 inches, and penetrate is considered the SPT standard penetration test n value, which is the reflect the degree of dense, which is relative density of cohesion soil, reliable. Also degree of firm, which consistency of cohesive soil, not always reliable. The content correction are required for a SPT below 60%. Standard energy drilling equipment method correction CF60 is applied to the both cohesive clay and cohesionless is sand, or CL2, which is obtained by correctionless CF1 is obtained the application cohesion. I will explain the example of SPT as a bend shear test. I am escaping here the penetration and dilatometer and overturning also. Overturning also. Okay. So this is another SPT for silt and clay CF60 and FN CF60. The example, this is the formula we have given, and SPT for silt and clay BSRM. This is BSRM and divided by 60 and NF. The 100 when the overburden pressure is PSF, then it will be used to 2000. On the other hand, if you this is not PSF, the value will be changed. For the clay CF60, so into NF there is no correction factor. If there is a correction factor, there is no correction factor. SPT for clay the BSRM, consequently BSRM and divided by 60 and NF, but there is no CF. Okay, we can see here another is 1 kPa 20.86 psf. So this is an example is given. The SPT correction factor N60 is correction SPT value, so 60% energy, and drilling equipment method associate parameter 60% energy and drilling equipment correction for field SPT. The correction coefficient less N60 equal to CF correction factor of 60 into NF. N60 is corrected SPT value for 60% energy and drilling equipment method. CF60 is a correction factor for 60% energy. Okay, NF is a field SPT value, and this is our main formula. BSRM we will remind this 0.60, and the EM is a hammer efficiency and do not catch, which is 0.52 and 60. CB is correction borehole number. 1 for dia is 2.5 to 4.5, 1.5 for dia when the dia is 6 inches, 1.15 for dia when the dia is 8 inches. CS is a correction sampler, 1 for standard sampler, 1.2 for a sampler without liner. CR is a rod length, 0.7 for L where 3 to 4 feet, 0.85 for length is 4 to 6 feet, and 0.90 for length 6 to 7 feet, and 1 for is greater than length of 10 feet. So this is the formula for overburden correction. We have seen here N160 is CF60 into C1, CF60 is CF 600, CF root over 2000 divided by overburden pressure. If the is PSF, on the other hand is kPa, then 100 divided by overburden pressure. Okay, here is the Q and C subsurface strata. We know the C equal to Q divided by 2. C is 300, N160 it is used, and N60 percentage of the correction value. Phi equal to 15 plus root over 220 and 160, but we will use another example also. So this example we have to understand. This is our last what I will say, this is the last example, and this is the last portion in our example. The relative parameter of proclaim in class PPC, we can see the geotechnical site investigation was conducted at site in Dhaka, which is Bangladesh, beside the India. A hammer having the efficiency is 52% was used. The drilling operation and field blow count for the subsurface stratigraphically as the obtained at the site of the particular boring and summarized in the following figure below. The figure is given here. Determine the field SPT below for all depth and apply necessary correction 60% energy overburden, and that calculate the correction SPT value as required at approximately as necessary from the SPT value as various depth. Note that the drilling crew stream forget to the boring line, and the entire site of SPT test were conducted without liner. So this is our flow without liner. So you can see here EGL, the elevation is 0, 5 feet, 4 feet, 5 feet, 10 feet, 13 feet, 15 feet, and 20, 25 feet also. The first strata is dry zone, second is the shale clay, and another was just steadied foul clay. Okay, so the blow is count 2, 3, 4, 3, 3, 3, and 3, 5, 5, and 4, 5, 5, and the unit weight of soil is given, the dry and saturated consequently. Okay, so let's start. So we know we'll calculate for first count for 5 feet below of the ground. So N160, because this is the sand, we can see here the sand. The formula will be CF60 into NF. What is CF? CF is BSRM, BSRM 60 into NF. and CF is overburden pressure. So we can see CB is 1 because the borehole diameter is 4, and CB is 1, the sampler without liner. So these are the given here. These are the given here. This is the this PSRM. This coefficient are also given for calculating purposes. And CB is 1.2 and R is 0.7 for 5 feet below the rod length, and EM 52 and NF 3 plus 4. Why we have taken the 3 plus 4? This is 3 and 4, and first portion is 2 is we are deducting, or we are emerging, and we are eliminating for the calculation purposes, as soil will be disturbed. That's why the 2 will be eliminated. Okay, so is a 7, and overburden pressure after the depth of 5. So you can see gamma into Z, and first gamma 92.4. So we can see the here as a 92.4, and depth and unit weight is already saturated minus dry water, and 4 to 9.6 is given here, and putting this value here, and found N160 is 11.78. So this is the an answer, and we can found the phi value also. At the depth of 5 feet, we use 20 into root over 20 N160 and found 35.5 degree. Consequently, we will calculate the for 10 feet. This is the 10 feet, and we have used the CB1 CS 1.2 R 0.75 EM equal to 0.52. How will get this? We have found this from the given chart. This is chart will be given in example in the exam center. And NF, how will get the 3 into 3? This is nothing but this is the 3 into 3, and first 3 will be eliminated. We will not consider the first 3 because the 3 is disturbed the soil. That's why we will not consider first blow count. Okay, and overburden pressure we have calculated in 10 feet, in consequently 739, and we can see here in this way we are calculating here and putting this value, and and found N160% 7.71, and for phi will be 20 to root over 20 N160, and found 32.45. And another one we can calculate for 15 feet. Here is the 15 feet. We can see here 15 feet. The blow is 355. We will not consider 3. We will consider 5 and 5. We will consider 5 and 5 here, and NF. And BSRM is given in example sheet, and we have found NF is 10, and consequently N160 is 8.84, and Nu equal to clay 333 into N160. This is the this is the formula is given. I have already shown here. 333 into N160. This is the correlation between NF and C, and found 2943, and C is found divided by 2, which is 1471.9 psi. And the last one we can see here is a clay CF 60 BSRM in NF. NF is 5.6. BSRM is given in example sheet, and NF is 5.6. I will get 5 into 6. This is the last two blows, so it's 5 into 6, and 4 is we will not consider 4 because the first blow is will be disturbed. That's why we will not consider. Okay, in this way we will found 10.87, and Nu will 333 and 60, and found 3619 PSF, and C will be divided by 2, and found 1809.8 PSF. Okay, so we can see this is the last example in our lecture, During the standard penetration test at 5 feet below the groundwater level, N160 was obtained for applying correlation for borehole diameter, hampering efficiency, rod length, and simmer as below. N160 is 10. Calculate N160 and compare the effective angle of internal friction at the depth of 5 meter estimated based on the both N1 and N60 and N1. So this figure in given we can see is a EGL and 3 feet, 6 feet, and 16 feet is given. So we can see vertical overburden pressure 5 feet. This is the 5 feet. N1 prime is 16 into 3 and 5, so 18.1 minus 9.1 and into 2. So 3 plus 2, that will be 5. So we will calculating for 5 and found 66.38 kilonewton per meter square. Now we'll putting this value here and found is given there the keep is kilonewton per feet. That's why we will use 100 divided by BC and found 1.29. When N160, then 5 equal to 20 into root over 20 into N60 and found 34.42. Another one N164 for N160, so remind that. Then the angle will be 24.96. So we can see the N160, the angle is reducing. Okay, so for cohesive soil, when the N160 is equal to Q divided by 2 and found 1731, and for N160 we have found 204. So this is also, I can say, the reducing. So thank you everyone. This is the boring lecture, as all the lecture is given for theoretical basis. I want to throw taking the math example for clear visible or clear understanding you. If you have any question on subsurface exploration, then let me know. Thank you everyone. And before leaving, I want to say the formula is given here. So this is the given formula. So if you apply this formula, so don't afraid, you can use this without hesitate. Thank you.